I formally welcome all the members on this sixth talk of this year in NASNI. And for the just information that our this NASNI group is National Astronomy Network of IAPT, and it is entirely dedicated platform under the Indian Association of Physics Teachers, and it is designed to foster interest and engagement in astronomy and sky watching among students and also educators and in general we can say general public also. And NASNI is actually created to bridge the gap between new sky gazers and experts from various institutes by providing structured learning and mentorship and also observational guidance in astronomy and astrophysics. And it mainly aims to nurture curiosity and promote scientific temper, and also to connect enthusiasts with the leading astronomers like you and astrophysicists and experienced sky watchers of our country. And our members organize workshops and observational sessions and star parties at different places where they are sitting, and they attract the society and students also for these parties. And sometime interactions with professional astronomers are also there from planetariums and research institutes and academia also. So that is the actually focus point of this NASNI. So on behalf of NASNI, as a coordinator, I welcome Dr. Arvind Subramanian from Indian Institute of Astronomy today. And we also have with us, our young enthusiast, Mr. Aryansh Saxena from Central University, NIT Hamirpur in Himachal Pradesh. And I will request now Mr. Aryansh to introduce our speaker of today's session.
Arvind Balasubramanian. So Dr. Arvind Balasubramanian, for those who don't know, is a postdoctoral fellow at Indian Institute of Astrophysics, Bangalore. His research interest involves study of astrophysical transients like merger of compact objects, supernovae, fast radio burst, fast X-ray transients, etc., using observations in the radio wavelength. Observational astrophysics involves acquisition of detailed data, analysis of obtained data, and arriving at meaningful conclusions based on the analysis. He began his journey into astronomy and astrophysics by pursuing BSMS dual degree at IISER, Pune. He worked at Texas Tech University for his PhD thesis on studying radio emissions from binary neutron star mergers GW170817. So it's my honor to share the stage with you, and it would, without spending any more time, let's dive right into the talk. Arvind sir, please, you may start.
Yeah, I'll just share my screen. Yeah. Can you all see the screen?
Yes, sir. Yes, sir.
Yeah. Okay. Yeah. Thank you so much for the invitation and this nice introduction. It's really an honor to present my work here. So I was talking to Sir before this, and he was telling me how NASNI is helping the physics community to try to understand what astronomy is, how research is happening. So it's a really nice initiative, and I'm happy to be a part of this. So yeah, I thought I'll just give a brief talk about like how I started working in astronomy, what excited me. So I decided to say that like how I started from stargazing and went on to radio astronomy. So similar to how Sir was telling just before this, that I am guessing many of us here are very avid stargazers. So I thought I'll just start from there. So this will be my rough outline of the talk. So initially I'll just talk about my amateur astronomy stargazing during my college days. And then I'll go on to the work that I've been doing from like my master's thesis to currently what I'm working on. So I mostly work on this thing called transient astronomy. We will get into what transient is in a few slides, and yeah, I'll end with a little bit of future prospects. Um, so just before we get into what stargazing is, um, why do we do astronomy or astrophysics? So this is a question that many of us are asked a lot, and it's sometimes slightly difficult to answer this question. But if we actually think about it, many cultures from all over the world, they've observed this regular motion of objects in the sky, like the sun, the moon, the stars, the planets, and so on. So this has always fascinated mankind. And one of the earliest ways of like measuring time, what if we didn't have any watches? It was to use the objects in the sky to tell time, and that was one of the most scientific ways. Like that, it is one of the most natural ways to find what the time is. Like you can see a daily cycle of day and night. You can see the monthly cycle of the moon changing its phase. Then you can see the yearly cycle of different stars rising and setting at different times over the years. So all of these things actually made many people all around the world. You can see different calendars all made based on the motion of sun, moon, and the other objects in the sky. So one of the main reasons why we do astronomy is that we have this curiosity, like how did we come here? What is the universe made of? Where are we in this universe? Um, what is our significance, and those kinds of things. So this is where one of these very famous quotes from this scientist called Carl Sagan comes in. So he's an American astronomer and planetary scientist, but he was, I think many of you might have heard of him from this very famous documentary called Cosmos, where he gave a very nice nice view of astronomy and astrophysics, beginning from the history of astronomy to more modern astronomy as people as researchers work on astronomy. So he says that the cosmos is within us. We are made of star stuff, and we are a way of the universe to know itself. So this is actually a very nice, nice thought-provoking quote. So I thought I'll just put it here. So apart from the main curiosity of how did we come here or what the universe is made of, there are other serendipitous benefits. So benefits that were not actually intended, like some things that began as solving problems for astronomy ended up solving problems which are much closer to us, like much closer to home. Like many of the healthcare technology, like MRI or CAT scan, those kinds of scans, many of those kinds of technologies were initially developed for astronomy, to analyze images, to take images of the sky, those kinds of things. Then communication. So for instance, the Wi-Fi that right now most of us cannot live without was actually initially discovered in like radio astronomy labs, like the CSIRO in Australia. So this was discovered to actually try to understand the radio emission from the universe. So yeah, there are many other serendipitous benefits, like the LASIK surgery for the eyes. So many technology that was that is being used right now for the eye surgery was actually developed for like adaptive optics for telescopes and those kinds of things. So yeah, so I'm hoping that I gave you an idea of why we do astronomy and astrophysics. So for me, my interest in astronomy started like with stargazing, like most of us. So I was doing my integrated masters at ISER Pune. So that's when I I got to know about this amateur astronomers group called Jyotirvidya Parisamstha. So they used to organize this all-night stargazing sessions. They were actually very, very interesting, and they were something that I tried to attend as much as possible. So what they used to do is they used to choose a night where the moonlight is very less. So around the fourth day after new moon, or the fourth day before new moon, and and they used to uh, arrange a pickup from the main bus stop in Pune, Swargate bus stop. So they arrange a vehicle to pick you up from there, take you to a place that is around 70 kilometers from Pune, which is somewhat of a low light pollution area. So they took us there, gave us dinner, and then there were short lectures about the sky, how stars move, what are the different objects in the sky, and then there were a few telescopes set up that could that were put on like very nice objects like the planets, the moon, and then some other interesting deep sky objects. So I got very interested, and that made me actually get my own telescope. So I got my own telescope. You can see my telescope here. This is one of the pictures that we took in one of the stargazing sessions that we organized for school children in ISER Pune. So we started organizing these regular stargazing sessions. I started learning a little bit more myself, looking at videos online, and asking people around. So that's how I started learning a little bit and doing a little bit of amateur astronomy. So we also, I was also the joint head for the ISER Pune Astronomy Club. It's called Akash Ganga. So we had these very nice stargazing sessions and talks, somewhat like this, which were organized to help students like get exposed more about to more things about astronomy, to how research is done, and so on. So yeah, along with stargazing, I also started doing a little bit of amateur astrophotography. I'm not very good, so yeah, I think I'll just skip this slide for now. But this is a picture of the moon that I took with my phone and attached to my telescope. Yeah. So if there are questions, I think you can put it in the chat box, and I'll try to answer. Yeah. So like I said, many different cultures began observing the sky, and so although astronomy began with the optical wavelengths, it is not limited only to the optical wavelengths. So now with the last 100 to 200 years, 200 to 100 years, we have been developing various new instruments to actually observe the universe, that is, see the universe in other wavelengths. So here is a nice cartoon of the different parts of the electromagnetic spectrum, the different wavelengths, and which parts of these electromagnetic spectra can we see from the Earth. So the plot here on the y-axis shows the atmosphere, and if the lines from the sky are able to reach the Earth, that means that those wavelengths we will be able to observe from the Earth. So if you see here, there is an optical telescope. So there is this small window bit in the UV and the IR which reaches the Earth, and we have many ground-based optical telescopes that can observe in these wavelengths. Then we have this huge chunk of the radio wavelengths which also reach the Earth, and we have these radio telescopes which are also ground-based. Now, if you also notice that some of the, if you see, the optical telescopes are actually placed at higher altitudes, because if we go slightly higher than the troposphere, the variations in the atmosphere are not so much, and so we'll be able to reduce the different artifacts that variations in the atmosphere causes in our images. So most of the optical and parts of UV IR bands, those telescopes are placed at very high altitudes. Now there is a big chunk of this electromagnetic spectrum that does not reach the surface of the Earth. On the left we have the very high energy gamma rays, and on the right we have the longer wavelength radio waves. Now it's a good thing that our atmosphere protects us from these high energy waves, because a lot of UV or anything to the left of this is not exposure to anything to the left of this is not very good for us. So we should thank the atmosphere for it for protecting us. But if we really want to observe the sky in these wavelengths, we need to go to space. So we need to go outside this thermosphere area. So so many of you must have already seen very nice images of the optical sky. So by just going above the atmosphere, even with a small telescope, we'll be able to make a big difference, and that's what Hubble did. So it's one of the best instruments till I would say the last 2-3 years in the optical to in the UV to IR regime, which was imaging the sky. It's a it's a satellite telescope that was launched by NASA, and almost any good image of the sky from the planets to any of the big objects that you have seen, maybe about 2 years ago, were taken by Hubble. And then we also have the newer instrument that was launched very recently called JWST, the James Webb Space Telescope. So these two telescopes are one of the best telescopes in this region. So the other telescopes that are shown here are the Swift and the Chandra telescopes. So yeah, we have different telescopes that work at different wavelengths, and for the wavelengths that don't reach the surface of the Earth, we need to go out. So we have these different instruments. So yeah, like I said, so I started with stargazing, but slowly I started moving to doing more research work during my master's itself. So the main things that I work on, the main objects that I work on, are called astrophysical transients. So what are these transients? These are phenomena that change their emission over relatively short time scales. Now what does this short mean? So we'll just get to that in 1 second. Just a disclaimer: I've made this image, these images with AI, so Notebook LM, but they are somewhat illustrative of what I want to say. So we don't have, I mean, these are just for examples, so they need not be taken as very solid, because we can, okay, I'll just get to that in a second. So transients are mostly divided into two broad categories called extragalactic transients and galactic transients. So these galactic transients are transients that occur within our galaxy itself. And why I mean to not take this image very seriously is that there are a lot of supernovae that have been seen within our galaxy also. So both of these, objects that have come here can also come here, and objects that are here can also come here. So yeah, that's just a disclaimer. So there are a lot of these different objects called transients. So anything that changes their emission over relatively short time scales. So what does short mean? So I've given here a range of possible time scales that we see. So these are just examples of transients. There are these different examples. We don't need to get into what they are right now. They are just, we can just think of them as different kinds of transients. They are different because they primarily emit in different frequencies. So you can see that there are these objects called fast radio bursts. So we'll get to them a bit later. But they primarily emit in radio. And then there are these things called supernovae. They primarily emit in optical and X-ray, but they also emit in other wavelengths. The primary emission is in optical and X-ray. And then there are these things called tidal disruption events, which emit in UV or soft X-rays. So yeah, for the time scales itself, so they vary from the order of milliseconds to the order of a few years. So that's what I meant by short. So short in the astrophysical timescales, like in the timescales of like the age of stars, the age of the galaxy, or timescales over which galaxies evolve or stars evolve. So these are very short compared to those timescales. So these are what are called astrophysical transients. So just to name a few examples, so there are these things called novae, where um, um, when some of the massive stars they become after they have lost their ability to fuse more material, they collapse in different fashions. So some of them make if they are not very massive enough, they make things called white dwarfs. Some of them when they are slightly massive, they can make things called neutron stars. All of these are very compact stars. They are not very bright in the optical, but they do have signatures in other wavelengths. And then if the star is very, very heavy, then it can make something called a black hole, which I think many of us are familiar with, at least in the very general sense. So yeah, massive stars can form many compact objects once they have stopped their fusion. And so novae are these binary systems where there is one white dwarf, one of those compact stars, along with a regular star. So what this compact star is doing is it is starting to pull material from this regular star. And when material falls, at some times, some thermal processes occur on this white dwarf, and there's a sudden outburst of emission. So that's called a nova. So it causes bright flares by white dwarfs. Then there is this thing called supernova. So as I said, if it becomes slightly more massive, then it makes a huge bang kind of thing. So it's called an explosion, and it throws out a lot of material, and it forms something called a neutron star or a black hole, depending on the mass of the star. Then there are these new kinds of events called multi-messenger events. We will get to them after some time. But as I said, if there is very heavy stars, they form these things called black holes, and it has been hypothesized and theorized that most massive galaxies should have a very supermassive black hole in the center, around which like the entire galaxy is supposed to be rotating, and this black hole can emit material outside in the form of jets, and these jets are called AGNs. These are called active galactic nuclei. This also happens in some similar fashion like this, but on a higher scale. So there is accretion onto the black hole, and that causes jets to be launched. So this has actually been seen in many galaxies already, and so now we know that most galaxies, including ours, has a supermassive black hole in the center. So yeah, with that introduction of astrophysical transients, we can go into one example. Why I'm choosing this example is that it's not, there is no particular reason, but this is a very nice set of subclass of transients which have been studied for a very long time, and we do have a few nice insights into how these things form. So a gamma ray burst is a burst of gamma ray emission. So in the gamma rays, if you make a plot, I will show a plot maybe a little later. Just a second, I have a plot here. So if you see this plot on top here, this is the gamma ray counts. That is, you can think of it as brightness in the gamma rays as a function of time. So you see it's very flat, and then suddenly there is a peak. So this is what is a gamma ray burst. There is a peak in gamma ray emission suddenly. Now we talked about the time scales of those different transients. So these gamma ray bursts, uh, they generally last for between like a few seconds to about few minutes maximum. Okay, so there are these shorter time scale events, and they are called short gamma ray bursts, and then there are longer time scale events which are called long gamma ray bursts. So what happens is, so this happens with massive stars when they so there are two different mechanisms in which a gamma ray burst can be produced, and this was thought to be because of the two different kinds of gamma ray bursts. We just talked about the short and long gamma ray bursts, right? So it was thought that this hypernova or supernova scenario, wherein a massive star explodes and then collapses into a neutron star or a black hole, that it was thought that that is one of the reasons why we get these long duration gamma ray bursts. Whereas when we have these compact objects that we talked about, the neutron stars, when there are two neutron stars, when they merge, when there are two neutron stars which are very close, because of gravity, the gravitational pull between them, each other, they start to come closer and closer, and they'll merge into one. When they merge, they can produce short gamma ray bursts. This is what was thought, but I think recent research is showing that either way is possible to produce these short or long gamma ray bursts. But yeah, so we can produce a gamma ray burst with two different ways. You can have a supernova, or you can have merger of compact objects, and then we have this emission of gamma rays. So once this compact object is formed, it launches something called jets. So these jets, when they have different blobs, they collide, and when they collide here, they start to produce gamma rays. So this is what we see as the gamma ray burst. But at a later time, what happens is this material in the jet starts to hit the medium outside, the interstellar medium. And when it hits the medium outside, it produces something called the afterglow emission. So the afterglow emission is visible in almost all wavelengths, like from X-rays to radio. So from the highest energy to the lowest energy, or the lowest wavelength to the highest wavelength. So yeah, so with that introduction of transients and gamma ray bursts, here's an overview of my work in transients. So I have just divided it into three parts. So first I'll talk about my master's work, then I'll talk about my PhD work, and finally I'll talk about what I'm doing right now after PhD. So yeah, for my master's work, so I worked on localizing transients. So what does localizing mean? So localizing means trying to find where this transient has come from in the sky. So since transients are these events that are very short in time, it's very hard to actually detect these events. You need to have many of these telescopes or instruments. They should be very large field of view, because they need to be looking at almost as much of the sky as possible, so that you catch a transient. You don't know when a transient will happen and where in the sky it will happen. So there is a need for instruments that have very large field of view. But what happens is, once we have very large field of view, we have to sometimes compromise on how well it points. So it will have a very large field of view, but it will not be able to tell where the source is shining from. So for instance, we have seen there are many of these famous large sky monitors, like the Fermi gamma ray burst monitor, or some of them. So what these do is they look at a very large region of the sky and look for those gamma ray bursts that we talked about in the gamma rays. So what it does is, it will say that once it sees a gamma ray burst from some, say a gamma ray burst went off there, and Fermi was looking at this part of the sky, Fermi will say it came from somewhere in this big region. It will not be able to say exactly where it came from. And how big that region is, that depends on the different instruments. So what I did was that I worked on, I was part of this team, the team that works on this instrument called, okay, there is a message in the chat box. Uh, how the camera was attached to the telescope. Which telescope are we talking about, sir?
You have shown in the starting that you have taken some photo of moon by attaching.
Oh, that was from my phone actually, like my phone camera. So I just attached it to my telescope.
Okay.
There are these phone attaching mounts kind of thing. You can attach them to an eyepiece and then fix your phone on that and then take pictures. So yeah, I use that. Yeah, so I was part of this team that was working on this telescope called cadmium zinc telluride imager. It's an X-ray telescope, and it's on board this satellite called AstroSat. So AstroSat is India's um, first space observatory. Sorry for the typo here. It's the first space observatory dedicated for astronomy. So all the instruments here were only for astronomical purposes. And the idea here was that there were different instruments that were all pointing at the same region in the sky, and they were all at different wavelengths. So there was a UV camera, there was an X-ray camera, and there was another UV instrument. So there were instruments in spanning a large wavelength in the electromagnetic spectrum, so that you can actually take simultaneous data in different frequencies and try to understand what is happening. So that was a very nice idea. So I worked on this instrument. It's called cadmium zinc telluride imager. What this instrument is, if I have to explain it in just very simple terms, it's like a pinhole camera. I'm not sure if people are familiar, but if you have just a pinhole and you have a screen behind it, you'll be able to see the image of whatever is in front of the pinhole. But what CZTI does is it's a pinhole camera for X-rays, and it has many holes. So this is the mask, or the pinhole, if you will. So this mask is placed on top here. Then there are collimators, and the detector is in the bottom here. Now, if there are sources at different directions on the satellite, if there are sources that are shining from different directions on the satellite, that pinhole will make different patterns on the detector. So one such pattern is shown here. This is shown with all pixels on the detector, and then the same is more pixelated. So resolution is changed just to observe like patterns. Like here we are not able to see, but here we are able to see that there is more brighter, more photons that are hitting the detector from this side than from this side. So what we did was that we made a simulated model of the entire satellite that's shown here. And what we could do is that we could create these kind of images, the images of what the detector will see for different sources. So what we did, we took this model and we shined light on this on our detector on the entire satellite from all different directions. So I've just shown an idea here. So if we place the the telescope in the center of this image, and we shine light from all of these points that are marked here from all over the sky, we'll be able to get what the detector observes. So we'll be able to, from the simulation, we'll be able to get what this looks like. Then from the real sky, we can look at from the real image. So from the real image also, it will look somewhat like this. So we'll be able to compare the real image and the different images from the different directions, and then we'll be able to tell where the source is shining from based on the pattern. I hope that makes sense. Yeah, so that was what I was working on. So trying to find where the transients are shining from. So as that was happening, one of the best and most studied events, I think, in the past in astronomy, in the last 10 years, say, not 10, around 8 years, is this event called GW 170817. What GW is it means gravitational waves. Gravitational waves is actually gravitational waves is actually a consequence of the general theory of relativity. So Einstein had predicted that any mass that accelerates uh, in space will produce something called a gravitational wave. Um, that is not that is not light, but it's somewhat similar to light in the sense that it travels at the speed of light and so on. So Einstein had predicted this in the 1915, and there was a lot of effort from the observational side to try and detect these. And there are these detectors called LIGO in the US. Right now, a new detector will also come up in India called LIGO. So right now there are two instruments in US. One instrument called Virgo in Europe, and one instrument called Kagra in Japan, who are all the similar kind of gravitational wave detectors, and they are able to detect these moving masses. So what they actually are detecting right now are moving like mergers of compact objects, because these mergers are actually very strong in the gravitational wave signal. But as these detectors become much better, they will start detecting other moving, like just singular moving masses, as the detectors get much better. So, what was this event? So, I'll just play a short video here. So, this was a event that was the merger of two compact objects, two neutron stars. So these two neutron stars were traveling around each other and they merged. Once they merged, they produced this small jet called the gamma ray burst, and then they also had a lot of emission very close to the remnant itself. So there is this lot of this emission which is almost spherically symmetric, but there is also this jet-like emission. So this is what happened. So there were these two neutron stars that merged, and they produced. What is amazing was that they also produced this gamma ray burst. So if you recall a few slides back, uh, I'll just go to that slide. We said that um, one of the ways of producing gamma ray bursts is the merger of neutron stars. This was actually just a theory till this event. So this is the first event that had conclusive proof where we detected both gamma ray burst and gravitational wave from the same object. This is one of the biggest breakthroughs, I would say. So um, um, this is like one of the best direct confirmations that merger of neutron stars produce gamma ray bursts. So we saw gamma ray burst from this same event. We saw in this video, and then there was also this gravitational wave. So what is plotted here in for gravitational wave is the strength of the gravitational wave in the color. In the y-axis is frequency, and the x-axis there is time. So there's this very nice blip. So this is what is called the gravitational wave. Yeah, this event, like I said, it's a literal gold mine. Like, it's one of the best studied things in the last 7 years in astronomy. And as I said, this was one of the events that verified that gravitational waves and electromagnetic waves travel at almost the same speed. Einstein's theory that gravitational waves travel at speed of light is verified now. We also as I said, so when massive stars, they stop fusion around iron. So elements that are heavier than iron cannot be formed within stars. So how do we get these heavier elements that we see? Like all of these elements that we have in our day-to-day life, like um, we see gold, we see silver, we see uranium um, in our nuclear plants. How do all of these heavier elements come? So we did observations of like supernovae were um, actually showed that some of these heavier elements are formed in supernovae, but it was also shown that not all heavy elements could be formed. Like some heavier elements could not be could not be formed in a supernova. So one of the theories was that even these mergers of compact objects will be able to produce these heavier elements. So the optical and infrared observations of this event, UV optical and infrared observations of this event itself, it confirmed presence of heavier elements like gold. So I mean, that's why we call this a gold mine. Like, it's literally where gold was produced in the universe. So yeah, just to let that sink in further, any gold that you see around you on the earth was made somewhere in a supernova or a merger of some neutron stars some time ago. That's really mind-blowing. And then yeah, and then there were many more newer things, like many cosmological constraints were made about cosmological constants and so on. But yeah, we can keep discussing this event forever if we dive into that. So I'll just go back to what we were talking about. So localizing transients. So what happens is that even gravitational wave detectors are not very good at localizing. I just want to check how much longer I have and how much I can continue. Hello, can you still hear me?
Yes, you are audible. Yes.
Yeah, how much longer do I have? Should I start wrapping up in around 10 minutes?
We have 10-15 minutes more.
Okay, sure. So I'll just start wrapping up a little bit more. So yeah, gravitational wave events, gravitational wave detectors are also not very good at localizing sources. So here, if you think of us sitting at the center of the sphere, the different bands here, patches, are the different region, localization regions, like where each of these instruments said that this their particular afterglow or the event was coming from. So if you see this thing named as HL, that is the two LIGO detectors in the US. They said that the gravitational wave event is coming from somewhere in this region. That's actually a very large region. For perspective, I think a full moon is just a point on this map, a point. So just to make it clear, so this is worth like hundreds of full moons. So this is a very big region. Then there is another detector called Virgo, which I said, which is there in Europe. So when data from that instrument was also taken, they were able to make the region slightly smaller. Then the gamma ray burst that we saw from Fermi, that gave a slightly larger region. But both of these were overlapping, you see. So ideally, our source should be somewhere here. This large circle that you see here, this is the circle. So as I said, AstroSat is a satellite. So we are above the Earth. But part of the sky is always covered by the Earth. We are not very far away. So it's a low Earth orbit satellite. So like roughly 1/3 of the sky is always covered by the Earth. You cannot see behind the Earth from the satellite. So what happened was that at that point, CZTI was looking at this particular event, GW170817, was shining through the Earth when the satellite was this side. So the satellite was not able to observe this event, but the data from Fermi actually said that this is a very bright event. So we would have been able to see it with CZTI. So given the fact that we didn't see it with CZTI, we know with high confidence that it is behind the Earth. So we were able to make this circle saying the Earth is so big in the sky. And now we see that all of these regions overlap. And finally they found the remnant of this merger within this region. So that was about the X-ray part. So once I was done with my master's, I went on for a PhD, and during my PhD I slightly switched gears and I started looking from X-rays which were almost towards the left, that is some of the lowest wavelengths. I went to the longest wavelengths. I jumped to the other side of the electromagnetic spectrum and I started observing this event itself in radio. So what I'm showing here is a cartoon of what happened to the event. So you remember we saw in the video that there were jets launched from the merger. merger remnant, there are jets. There is this thing called cocoon, which is just the jet choking with the other material. The other material is not allowing the jet to freely come out towards the medium. And then there's this other material here. So the gold that was detected in the UV optical IR came from this material, the circular material that you see here. So this is what is called a kilonova. So this material is what was producing the UV optical IR emission. But the X-ray and radio emission itself was coming from this this choked material. This is so these are the slowest material. These are medium speed, and this jet is very fast. So they are at relativistic velocities. So what happened was that when so here we had observations in almost all wavelengths, but I am showing only the X-ray and X-ray which is from the Chandra in this color, and the white color is the VLA radio emission. So what I'm showing here is that. So this slow rise of this so what I'm showing here is the brightness as a function of time. So the brightness of this object slowly was rising in the X-ray and optical for a long time. It took almost a year for it to peak. So this slow rise actually told us that there are different velocity material from like slowest velocity to highest velocity. Once this peaked, we were able to know that this jet was able to bore through. So the jet which was initially not able to freely come out towards the medium slowly was able to push the material away and come out and interact with the medium. So that's what tells us that the jet has interacted, this peak. And then this decline tells us that now there is the jet has peaked and it's slowly interacting with the medium and it'll start slowing down. So everything else will start decreasing. So the brightness will start decreasing with time. So this is what happens. So the jet is interacting with the medium and we are getting the X-ray and the radio emission. The position of this peak itself tells us where we are observing from. So these radio and X-ray observations were actually very, very critical in telling that we are actually observing slightly off from the axis. Like the GRB is going in this direction and we are observing at around 30 degrees away from this axis of the jet. Yeah, so now we have been able to see the radio emission from the jet itself. What I did during my PhD was that once this jet has slowed down enough, it will become very dim. You can see that it's starting to become very, very dim. What will happen is this other ejecta, which is slightly slower, will also slowly catch up and start interacting with the medium. So that will again start producing X-ray and radio emission. So my idea was to try and look for that emission. So if you see these last 2 points here, so what I see is that we still are consistent with the jet only decaying. So we still don't see this material coming and interacting with the medium. What that allows us to do is that we can actually place different constraints on the physics, like how these ejecta here are energized. What is the physics of the neutron stars that collided in the center? Those kinds of things. So because we don't have too much time, I'll just not explain this too much, but if people have questions, I can get back to this. The last thing I'll just talk about for the next 5 minutes is this thing called fast radio bursts. So we talked about these short gamma ray bursts. We talked about them being like a few seconds to a few minutes long at the maximum. But fast radio bursts are much more recently discovered phenomena. So these are extremely bright bursts in radio. So if you remember, we saw this gamma ray burst in few slides before. This is something similar to that. So again, if you plot flux versus time in the radio, you again see some flat values, and then suddenly there's a spike, and then it again becomes flat. So what happens is that these radio pulses that we see, these are not pulses. It's better to call them as bursts. So because they don't repeat, I'll just get to that in a second. But these are very, very bright bursts in radio. And if people are familiar some of the brightest objects that we have seen in our sky are some things called pulsars. So they are these neutron stars that rotate, and they have a jet which points to us at different times depending on how they are rotating, like a lighthouse. And these rotate at like millisecond kind of frequencies. These pulsars actually are very bright, but if you see these fast radio bursts that we have seen are about 10 to the power 10 or 10 to the power 12 times the brightness of these pulses. So you can imagine how bright they are. They are very, very bright in the radio. The reason why we have discovered this very recently is that they are very short and it's hard to discover them. So the duration of this burst, if you see here, is a few milliseconds actually. So if you see the x-axis, this the time is given in milliseconds. It's around less than 100 milliseconds. So these are very, very short. And the plot in the bottom is something similar to here. The plot in the bottom here is something similar to what we saw in the gravitational wave. So there is frequency on the y-axis, time on the x-axis, and the brightness, the color, the brighter regions show more flux density. So yeah, so now one thing that we observed is that in this characteristic plot, you see that the higher frequencies arrive earlier than the lower frequencies. The lower frequencies arrive at a later time. So, so if we read up about pulsars, you will actually see that this particular separation, the degree to which this shift happens between the time of arrival of this higher frequency and lower frequency, that actually tells us what the distance of this source is. It's a proxy to the distance. So if we see for all of these fast radio bursts, we see that most of them are coming from extragalactic distances. They are not from our galaxy. And a lot of events have been discovered till now. Around 4,000 events have been discovered. Slightly greater than 50 of these events repeat. I'll just get to that in a second, what repeaters are. Based on observations till now, we know that these events are very, very common in the sky. Around 800 such events occur every day in the entire sky. That's a lot. And what was very, very nice was that one bright burst similar to this fast radio burst was seen from a galactic magnetar. So now what is a magnetar? A magnetar is a neutron star with a high magnetic field. So this is the name of that magnetar. So this made the community that was actually observing the fast radio burst to think that maybe magnetars are producing these events. So what are these events actually? The origin of these events are still an open question. They are very close to being magnetars, but they can be many different things also. So there is this very interesting page called the FRB Theory Catalog. You can go to this page and look at these events, the different possible mechanisms in which fast radio bursts are produced. So I've just given a cartoon of a few of them here. So there is this thing called star quake or magnetic field reconnection, wherein magnetic fields snap, and as we know, magnetic field lines cannot cross each other. So when they snap, they rearrange magnetic fields, and because of rearrangement of the fields, a lot of bright emission is emitted. There are also very weird models like this, where you have some asteroids passing through the magnetic field of a neutron star. There's also this where we talk about a merger of compact objects, like that neutron star merger, which we talked about, GW17081. So based on observations, there are seemingly two different populations. There are some events that repeat, but the repeating events have no periodicity. So they repeat very randomly. Some of them repeat a lot. Some of them don't repeat. They repeat only very less. There are others which did not repeat at all. So we have seen just one burst from that region in the sky. So we are not sure if there are different. So if there are different populations, are there different mechanisms? Like, can repeaters be explained by this? Whereas merger happens just once. So maybe this is a possible explanation for non-repeaters. We don't know. So the community right now is trying to study fast radio bursts. They are trying to find. So we talked about localizing transients. So again, we need to localize fast radio bursts, and then we need to study the environment of fast radio bursts to try and understand what they are. So I'll just take last 2 minutes. Is that okay?
Yes, 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 yes. You can finish.
Yeah. So I this, and I have just this slide and the one more slide. So just to give you an idea about these fast radio bursts, so I have been working on this one event called FRB 190520b. So this is a very nice event because this is one of the handful events. There are very few. So I said around 4,000 or 5,000 events have been discovered. But out of these, only like 3 or 4 events have been discovered with something called a persistent radio emission associated with them. What this means is that the fast radio burst occurs at very short durations, as I said. So the pulse, the burst that you see it only for a millisecond or so. But what happens is that for this particular event from the same region, there is also a continuous radio emission that happens, which is much lower. So when this source emits a fast radio burst, the fast radio burst becomes much brighter than what is seen here. But this is what is this persistent radio source, which is there when the burst is not seen. I hope that is clear. So what happens is that this particular event was, they were able to localize it. They found a host galaxy which was star forming. They found that this persistent emission is a compact source, and the spectrum that is plotted here, frequency versus brightness, is somewhat flat. It's not a steep spectrum. Then what was seen was that if you see these different colors here, this is the spectrum taken in 2020 and this is the spectrum taken in 2021. So what we see is that there is a decrease in the total brightness of this source in almost all frequencies as time went on. So what we did was that we saw this model called the Magnetar Wind Nebula model. So this is a model that explains both how FRBs are produced, how fast radio bursts are produced, and also the persistent emission. So because I don't have too much time, okay, I'll just try to explain this in like 2 sentences. So there is a magnetar here which was formed after a supernova. The supernova ejecta is shown in this dark color here. But what this magnetar does is that it has some activity. So it tries to do some magnetic activity, and because of the magnetic activity, it makes some shocks. So this shock actually blows something called a nebula within the ejecta. Okay, the nebula itself is producing the persistent emission, and this activity of the magnetar itself is producing the fast radio burst. But what this model actually says is that this magnetar has to be very young. Only young magnetars are very energetic, and they do this they have this chance of making this activity that produces this fast radio burst or this persistent emission. So what we did is that we got more radio observations, more than what we saw before at late times, and these different colors are at different frequencies. You see that there is a slow decline in almost all frequencies over time. So what we were able to show is that we can guess the age of this magnetar. I said that magnetar which was in the center is supposed to be a young magnetar. So we were able to guess the age of this magnetar. So there were also previous guesses, but this is with more data at late times. So this agrees with almost the other previous guesses. So the other previous guesses were that it should be between 9 and 100 years, and we get around 50 years. So more observations will actually improve this. So what I show here on the right is the spectrum. Again, you see the different colors are the different epochs, the times. So 2020 to 2024, you see that there is a slow reduction in the flux density. We also had low frequency observations from a radio telescope which is from India called GMRT, and this actually showed us that there is a show here that there is absorption, but we don't have deep enough observations to actually give points. So we will be observing this more to understand the physics. So what absorption does is that it changes how how the material is visible to us. Like for some frequencies, the material within is not visible to us. So that's what helps us understand how this. Yeah. So by studying this persistent emission, hopefully we'll be able to actually tell what the origin of these fast radio bursts are, or at least for those that have persistent emission, we'll be able to say what the origin is, because there are different models that predict this persistent emission. So we can make continuous observations, um, fit those models and see if we get like physical interpretations, like if we can get numbers like this age of the magnet or so on. So yeah, I think I will end with that and I can take questions. I'm sorry, I think I overshot by like 5 minutes.
Thank you so much, Dr. Arvind, for this enlightening talk, starting from your sky gazing experience and to be becoming a very advanced astronomer, professional astronomer, doing so much research. I thank you very much and see you in another talk on third Wednesday. Thank you very much.
Yeah.
Thank
Thanks
you.
a lot for the opportunity.
Thank
I'm
you.
very happy to meet all of you. Thanks a lot for
Thank
the
you so
opportunity.
much. Thank you.
Yeah.
Now I
Thank you.
sign off. Thank you.
Thank you.